So the three things I wanted to review, because they're going to come back up again, is regression, logistic regression, and then factor analysis. And these are sort of shorter, there's less slides on these, but it's possible that these are actually maybe more complicated. I don't know. So what is an odds? All right, and then odds ratio, and then what's a logit? Now we're like, this is all stuff you probably try to repress. Now it's all, you gotta try and bring it back now. You gotta unlock those memories. You gotta do some hypnosis or something. So what's an odds? What's another word for odds? Yeah, that's it. Odds is just probability. So odds is the same thing as probability. What's an odds ratio? It is, but the probability of what over what? I think I know what you're talking about. That's not this, but there is a reference to when you're comparing the probabilities of different events, you can use odds ratios to compare them. That's not this, but I know what you're talking about. So it's a ratio of odds. Obviously, it's an odds ratio, so it's a ratio of odds. But what odds? So this is where the language gets a little funny. We talk about, so if you think about P, here, we'll just make it very, very explicit. If you think about S being the probability of success, let's even do it this way. The probability of success, whatever success is. If it's the odds of, if you're flipping a coin and you're talking about the odds of getting it a heads, that's the thing you're trying to get. So a success then would be to get a heads. Over the probability of failure. I love the language, it cracks me up. Which is really just if this is the probability of success, then this is just 1 minus the probability of success. So how likely are you to succeed divided by how likely you are to fail? Something like a coin flip, if the coin is fair, the odds ratio should be equal to 1, because it's 0.5 over 0.5, right? So the odds ratio is 1. It means it has a 50-50 chance of occurring, right? As the odds increase, the odds for success increase, you're going to get numbers that are larger than 1. As the odds for success decrease and drop below 0.5, then you start to get odds ratios that are less than 1. So in terms of odds ratios, having a value above 1 means you're more likely to succeed. If you have an odds ratio that's less than 1, you're more likely to fail. So then quickly, the last thing, what's a logit then? It's not a logit. It's a logit. What is the word logit short for? It's a good guess. Logistic regression. Not quite. We're going to use logits in logistic regression. Not quite the same thing. So it's the natural log of this of the odds ratio. Odds ratio. You take an odds ratio, you take the natural log of it. That's the log of the odds ratio. That's a logit. The natural log of the odds ratio. So again, oftentimes what you see is that success is labeled P and failure is labeled Q for whatever reason. So I take the natural log of that, where this equals to P over 1 minus P. That's a logit. We spent time sort of reviewing these terms last time, just as a quick rundown. Sort of odds is basically the same thing as probability. It's often used differently, like a 5-to-1 odds, right, or something like that. But 5 to 1 odds is roughly the same thing as sort of 20%. Anyway, but the trick here is to go from an odds, which is like a probability, that if we take the probability of success of something, divide that by the probability of failure, which is just 1 minus success, we can form an odds ratio. And then once we get an odds ratio, we can take the natural log of it to turn into a LOGIT. And of course the question is, well, why? Why do all that stuff? The answer is because probability is nonlinear, right? It's a curvilinear function where we don't have continuously changing scores, meaning that probabilities are not scored on an interval scale, right? To go from 10 to 20%, you're doubling your probability, or 0.1 to 0.2, but going 0.8 to 0.9 is just a small increase in probability. So it's a very nonlinear scale. So by doing this conversion from probability to LOGIT, we can create a much more linear scale where if you start down very small, 0.05 probability, and we take that divided by 1 minus that probability, right? We get this 0.053, and we take the natural log of that, it turns that into a negative 2.994. Right? So it actually stretches it out. And it keeps going, where if you notice all the values that are below 0.5 being the midpoint of probability, right? 50-50. It actually ends up being, 0.5 over 0.5 is 1, and the natural log of 1 is 0. So it puts then that 0.5 in the middle of a scale that we're sort of used to. It becomes a z-score, like metric, where 0 in the middle, it moves in sort of z-like sort of values. And, you can keep going smaller and smaller, and this is potentially infinitely negative. And on the very top, 0.95, which is 0.05 away from 1, we're getting the same number, 2.994, as we get for 0.05 up here, but just negative here and positive down there. So what this does, it's maybe sort of hard to see it this way, but so if we take this curvilinear function, which is linear, maybe sort of in the middle, it becomes slightly linear looking, but on either tail end, you got very different changes in probability. And this isn't every item. This isn't what probability looks like for every single item. It's just a particular item. It's just generic. But if we take the odds ratio, divide all of the values by their all the probabilities for success over failure, we change it into this other sort of odd looking format where all of a sudden there's almost no change down here, and then it sort of has a huge spike. So what does that mean? If you look at the values again here, going from probability to odds, or probability to odds ratio is what this really should say. Going from probability to odds, what that does is if you notice, very little change up to, up through here, and then it starts to then blow up. It starts to get larger and larger, but they all stay positive, right? But there are much bigger changes above 0.5 than there are below 0.5. Right? So you got very little change below a probability of 0.5. Then after 0.5, the change starts to expand, accelerate much faster. So it's taking this curve and it's focusing on the top end of the curve, again above 0.5, and it's going to stretch this part out to be a lot more linear. So that's what it does here. So it takes, and it stretches that value out to have a more infinite linear sort of process. So it does that to one side by taking the odds ratio. And then when you take the log odds, it then stretches the whole thing out, both above and below 0.5, to being this perfectly linear function. So why is that important? Well, we know how to predict linear things. We know how to do stuff with linear functions. We have multiple regression for that. So if we can get it to look like a linear function and behave like a linear function, we can then predict this linear function, this LOGIT, and then convert back to probabilities to see how the probability is changing for each of those predictors. All right, so we're going from probability odds ratio then to this logit, this log, natural log of the odds ratio, to stretch it all out, make it linear. This process, there's a more general sort of term for this, is conversion. And I might have mentioned it last semester, but I'm not sure. This whole process, this is oftentimes referred to as a linking function. So we're able to link probability, these logistic functions, to a linear function through this sort of process, and then we can convert it back. So there's lots of linking functions. Logistic's not the only one. We do this for if you go into SPSS and poke around, there's these generalized linear models that have linking functions for all kinds of different types of distributions, whether it's like a binomial or point or Poisson distribution, or all these different distributions have linking functions that turn them into something sort of linear so that we can actually predict it, and then are able to convert it back and convert to things like probability once we actually have the linear function sort of predicted. All right, so we're using these linking functions to sort of make life a little easier in terms of creating a linear prediction of something that isn't linear, and then it'll allow us to then convert back and predict things like changes in probability from that function. Questions so far? Excellent question. We're going to get to that in just a sec. If you can hold on just a minute, there's a couple other slides that may help that a little bit. And then if I don't answer it, ask it again. Okay, so questions about how do we interpret the coefficients, because it is kind of tricky. And most textbooks and even places like Stata, their guidelines, they sort of take you as far as converting back to the odds ratio and then leave it alone. They're like, here's the odds ratio from the logit, but then what do you do with that? Right, we're not used to thinking about changes in odds ratios and things. So how do we actually deal with the coefficients once we get them? So we'll talk about that in a sec. So since this log of this odds ratio, where p is success, 1 minus p is failure, right? So if we take the natural log, that equals to something we're very familiar with. This is our basic multiple regression function that we do for linear regression. So in this format, what does it all mean? What are the b's? Yep, they're slopes. We're going to look at them and interpret them in this format in the same way. It gets a little funky because we're saying for a change of 1 unit in x1, we expect the logit, this whole thing, to change whatever the slope is. And of course, we're thinking, all right, well, why do I care about how much the logit changes? Because it's not really interpretable. So again, what it all means is that in this function, we can actually look at what's the intercept for the logit, what is the slopes relating all the x's to the logit. But the real question is, well, how do we get back to an odds ratio, to probability? And it's just a matter of going backwards. If to go from p, we convert that to the odds ratio by taking p over 1 minus p. And then we convert that again into the logit by taking the natural log of that p over 1 minus p. All right, so how do we undo that? What would be the steps to undo this and get it back to p? Just take the steps sort of backwards. How do we get rid of the natural log? Remember, this is the logit value. How do you undo a natural log? Exactly right, with the E button. So there's E is the anti-log. All right, so the natural log, anti-log. These are oftentimes on the same button in a lot of calculators, where one is the button, the other one's like the shift, and that button oftentimes will go together. So if I take E and I take E and I raise it to the value of the LOGIT, that will then give me back to the odds ratio. All right, so this equals then back to odds ratio. Because I'm basically taking the natural log off of this, so I'm getting it back to the odds ratio. And then how do we go from the odds ratio back? This is the odds ratio. I get it back to probability. No, because we want to get rid of the natural log, so not the natural log. We just got rid of that here. I don't want to put it back in again. So if I'm taking something over 1 minus something, if I take the odds ratio and then over 1 plus the odds ratio, it'll give me back to P again. Okay. So I can step back out again and convert my LOGIT to an odds ratio, right? And then take the odds ratio over 1 plus that value to get back to probability again. So what happens in a lot of programs, they typically just give you, they do the first step of that. They'll give you the LOGIT, right? They'll give you the B values, just in LOGIT term. And that's where you're going to see tests for significance. They're going to give you a standard error. They're going to divide. You're going to get like a T or something similar, a Z. They're going to tell you if it's significant or not. And then they'll give you another column that says the odds ratio. And that's sort of it. And they stop there. So you can interpret the odds ratio, but it's sort of difficult. You know, okay, if it's above 1, that means it's increasing in probability. If it's below 1, it's decreasing in probability. But where the LOGIT will actually have values. So if you actually look at the coefficients, it'll tell you that it's negative or positive. Right? So whether you're increasing or decreasing your odds. But the odds ratios are sort of difficult to interpret. And the reason why they stop here is because it's really difficult to interpret how the probabilities work. Because the probabilities are going to change. It's not consistent. The probabilities are going to change depending on where on the predictor you're talking about. Go back to this picture again. This one. If I'm changing on the X predictor somewhere down here, I'm going to get very little change in probability. If I'm changing somewhere in the middle, it's going to change quite a lot. If I'm changing up at the top, it's going to change very little. All right, so it's not a constant change. So in order to figure out how the probability is going to change, you actually have to plug in actual values for X, like 2 different values. I want to know when X is 1 versus when X is 2. See how the probability changes. When X is 5 versus when X is 6, and see how the probability changes. You actually have to work out where on the scale you're trying to look at the probability, like where on the predictor, and then compare different values to see how the probability changes. So we did that a little bit in Psy534, where we set up like, all right, here's the different predictors. Here's X1, here's X2, here's X3, and then we said, all right, so for number 1, and then we had, of course, the intercept value, and we sort of multiplied. We put numbers in here. Like at first, let's pretend like there's zeros for all these, and then whatever the intercept value is, it's the value of A, whatever it happens to be, and we would convert that over to a probability with those weights. And then that was, say, the first one, right, number 1. And then we did it again where we just changed one thing. This, and then we got a new probability, P star, and then we were able to compare P and P star to see how much that one change in X1 changed the probability. And then I could change it again to say 2, see how it changes again. You know what I mean? So the only way to actually figure out how much the probability changes is you actually have to plug in where on X you're interested in looking at, and then it'll tell you how much the probability is changing at that level of X. Down here it's going to change very little, middle it's going to change a lot, up here it's going to change very little again. So it becomes a lot more complicated, which is why they don't tell you the probability change, because it depends on where you're looking, right? So they can oftentimes they'll do this thing, they'll give you the odds ratio, but really to go the next step to get probability, you actually have to do a much more complicated comparison. I've never actually seen in a textbook or anything anybody doing this. I literally was working on a project with students who were trying to decipher what it all meant. And I started laying this out, and it was the first time that these research assistants and I started to understand exactly how the probability was changing. So ever since then, I started to teach this process, even though I'd not seen it done anywhere, and I'm not sure why it's not something that's taught more regularly in terms of looking at how probabilities are affected by the model. But it does lead you to these sort of very complicated looking tables where you're comparing probabilities to one another. We start off with the intercept only. All right, compare the intercept only, how much probably change when I go up one level in X, next level of X, and you keep just adding rows and be able to compare the probabilities as they change. All right. Does that answer your question? You want to show you an example? We figured out, I mean, it doesn't necessarily matter a whole lot. These are just predictors of 4-year, 5-year, and 6-year graduation rates. And we looked at different things like being male versus female. Did you have to be remediated, even though they don't like that term anymore? But did you need extra work when it came to English or math? Are you an underserved student, first generation, Pell recipient, all that stuff? And then we include the intercept and the intercept or constant. So these are the actual, the B values. These are the values in LOGITs. And then here's the exponent of B, which these are the odds ratios, right? So we take this value, if I take negative 0.098 or 0.983. So if I do that, if I take 0.983 negative, and I take E and I raise it to that value, I get 0.374. That's why those match. So if I take this value and take the exponent, that E, and I raise it to that value, I get this exponent here. Okay? So these are just the values. So now to understand how the probabilities are affected, we created these tables, which show the different markers being introduced or not. So if we look at the first ones, so this is no markers, meaning by markers we mean we flipped everything so that they were in the sense of if you had a marker, it actually lowered your chance of graduation, right? So all these were sort of in that same direction. That's why it says male instead of female, or like first gen instead of later generations or something like that. So if you look across this says they have none of those. So these are basically all zeros on these predictors. So this is a intercept only model. And we say, all right, so if you have none of those things, none of the markers, and this is for plus 5-year graduation rate. I guess this is for 5 years. This is how much the probability, how likely you are to graduate in 5 years if you have no markers. Right? That's about 52%. All right, well, what if go ahead. Female, you passed the EPT. I'm sorry, wait. Yeah, so this is remediation. So you passed the EPT, you passed the ELM. You're not underserved, which means you're from either Caucasian or Asian groups. So because these are all scored 0, 1, so these are all zeros, which means that the only thing we have in there is just the intercept. The intercept tells us that if you have none of the markers, you have about a 52% chance of graduating in 5 years. So look at just adding in male. So just flipping male to 1, going from 0 to 1 on male, that changes the probability 0.167. It lowers it about 16, 17%. Make sense? So the problem is, if we're looking at all of them one at a time, which is the first, these, so you can see the bold yeses down to about here, it's changing one variable at a time. If this were linear, right, and I added in two together, like male and underserved, you'd expect to be able to just say, to add in the 0.357 and the 0.422 or something. Like, they would be sort of just, you can just add them together, but you can't. Look at them, you have to look at them together and recalculate the probability. So if you're male underserved, it actually drops it. So let's think about how much it drops it. 0.167. If you're underserved, it's 0.101, which is 0.268. Well, when I combine them together, the probability doesn't drop down a total of 0.268. It's actually something smaller because, again, they're not linear and they're not additive in that same way. That makes sense. We can't just add in the two differences here. We have to recompute. When I have both of those together, how much does the probability change? If I didn't pass EPT and ELM, right, it means yes on here, I can't just add in those two, 0.067, 0.066. Actually, it looks like it is, but it's not the same number. It's close. But EPT and ELM together drops the probability of graduation in 5 years by 13%, roughly. If you're underrepresented minority, first gen, and you're on Pell status, which is the three things that the GI 2025, the Student Success Initiative that the CSU started, those are the three things that they are most concerned with. It drops 13.5%. So you're going to lower your probability of graduation in 5 years by 13.5%. The reason why we started looking at this is because being male is more detrimental graduation than the combination of all those things they're concerned about. But yet they don't talk about that at all. Well, that's a whole different thing. But you can see this table is set up to show how the probabilities are affected and how the probabilities change based on which markers and which things you actually include. It becomes more complicated when the predictors are continuous because you have more things to change. But if you actually want to convert the odds ratio over to probabilities and see how they change, you actually have to look at them all sort of individually and collectively to see how it works. Yeah, relative to someone who has none. So this is obviously designed very specifically for the constant, the intercept value, to be the best case scenario, right? You have none of the markers. So if you think about it, if you're a female, so what does that mean? If you're female who passed the EPT, passed the ELM, you're either white or Asian. You're not first generation. It means your parents went to college, right? Or one of your parents at least went to college, and you're financially stable enough to not qualify for Pell, right? All those things. Best case scenario is about a 50%, 52% chance of graduation. That's crazy that all those things combined, but even with everything perfect, you're still only getting, and this is 5 years, not even 4 years, this is 5 years. You're still only getting about half of them are graduating in 5 years. Nuts. Right? And then as you add in these different markers, you can see how much it actually lowers everything. The part of this too was the way that it got reported in these student success reports. They were treating them all independently, which also drove me nuts. They were treating Pell status, URM, and first generation as all sort of independent things and reporting them, even though they're highly overlapping. So we were trying to look at them all together because there's no way writing this report out to for admin and other folks to read if we just left the values like this in terms of the just odds ratios. They would look at this and be like, I don't know what to do with this. This doesn't help me. Like, what does this do? Like, how do I actually do anything with those numbers? So, but people do at least maybe poorly, but they do tend to understand probability. So we converted them over to changes to probabilities for each one of those things, and then looked at the difference relative to the person who has the most, is most likely to graduate, which is when they have none of the markers. It's good just in general trying to understand logistic regressions, bringing it back to this and being able to compare those things that you are most interested in combinations thereof are going to give you the predicted probabilities for each of those, and then you can actually then look at the differences to your baseline model, which also they may change how you define what the baseline model is, because you have to then, that's going to be like your comparison group. So I could have picked a comparison group to be someone who has all the markers, like the worst case scenario, and then compared how much the probability is improved by taking markers away. I could have done it the other way around, but we decided to do it this way. I don't have a recollection why, but this is how we've been doing it. And then of course we also added in sort of how to interpret a lot of these values in here in the text and stuff. All right, let's go back to here. I think it doesn't need saying, but I'm going to say it anyway, that logistic regression is easy to do, right? Easy to run it, right? You can throw some stuff into SPSS or Stata or any program, and you'll get numbers out. But interpreting them is a lot more difficult than it is in a regular regression. And that's why, people tend to be a little bit more uneasy about logistic regression, because we're dealing with things like LOGIT that people don't really understand very well. And it takes some extra steps, some extra work to get you to a point where you can understand what's actually happening. And that's why I started doing these tables comparing, to the baseline value. So the question I'm hearing you ask is there a standard way with which to do that? Seeing as how I just made those up, I don't think there's a standard way. I think it comes down to who's the audience you're writing it to. And in terms of the student success thing, it was all written, even though they talk about not writing in terms of disparities, disparity language. It was all talk. The whole thing was about like opportunity gaps and achievement gaps. Was all about how certain groups are doing or not doing as well as other groups. So we thought, all right, well, what things are actually lowering or are making them less likely to graduate? So it was written in that sense. And again, we could have done the other way around and talked about the group that had the lowest probability and how each thing actually added to the probability, increased the probability. Like I could have started with males who didn't pass, and and had all the markers sort of set up, basically the bottom of that thing. I could have started with this row, all markers, yes, right? But I could have just flipped them all and made them all zeros, so that this becomes then the baseline. The probability for that is 16%, having all those markers. And then I could have looked at how each one of the markers being removed added probability. So the long story short, you don't even have to have them all be in the same direction, right? You could, depending on what thing makes the most sense. And down here, we even started to get weird things where, like in plus 6 years, all of a sudden there was a flip where if you had EPT remediation, all of a sudden now you were more likely to graduate than the baseline value. This makes no sense. This is talking about that exact process where if I want the probability, I need to take E raised to the regression equation that I have. This is the odds ratio. And then I'm going to divide that by 1 plus the odds ratio to convert that back to a predicted probability. So this then looks at the change in probability is not constant with constant changes of X. That's the thing we were just talking about. This means that the probability of a success, like Y equals 1, given the predictor, is nonlinear, and it's going to depend on where on X you're talking about. It's going to give you different changes in probability. Y makes it much more difficult to interpret. People can interpret, oh, it's significant. That's fine. And that's what we get from logistic regression. But then what to do with that and how to actually report changes and stuff, a lot of people don't really know. So it's not obvious how the regression coefficients for X are related to changes in dependent variable, and the model is written this way. So like change in Y given X depends on the value of X. So look at that S-shaped function that we're talking about here. And again, it depends. Down here, change a little bit. the middle is going to change a ton. Almost, linear right here in the middle. You get this sort of linear change. But up here at the top and at the bottom, changing very, very little, depending on where you are in this predictor. That's why you have to sort of look at it. And let's say you had a continuous predictor. The way I would look at that is, all right, let's say X is scored from 1 to 30. You don't want to do 1 versus 2, 2 versus 3. You don't want to have this massive table. I would at least look at one of the lower values of X, one of the highest values of X, and probably pick a couple in the middle. Be able to change, to look at how those values change the probability depending on where they are. So it's a matter of sort of picking it. A lot of people would suggest, based on the regression, multiple regression literatures, to pick the mean on X, and then maybe plus or minus a standard deviation either side, and then see how the probability of that changes depending on where you are on X. So you're not having to do every conceivable value of X, but at least some important values like the mean plus or minus 1 standard deviation up or above or below the mean. So the values of the regression equation, so if we take the simplest form, right, where you just have one predictor, single predictor logistic regression model, B0 and B1 take on these sort of different meanings. And it's the same when you have multiple predictors, but it's just easier to think about when there's just one of them. Where B0 being the intercept value is they call it the regression constant. It basically just moves the line up or down. So if this has a higher B0, higher intercept, it's going to, this whole thing is going to, if it's higher, it's going to slide the whole thing to the right. It's going to have kind of the same shape. It's just going to slide to the right a little bit. If the value is lower, it's going to slide to the left, right? So it's just the intercept now becomes this regression constant that sort of pushes the line up or down the values of X. The B1, the actual slope, it's interpreted the same way. It's the steepness, but it's measured right at the point, the sort of midpoint, right when it crosses that 0.5 sort of thing. It's sort of measuring the steepness of the slope at that point. If you take negative of the intercept divided by the slope, you get what's called the threshold, and that actually tells you where that point is. Where is this point where the line crosses that 0.5 region, or 0.5 point in probability? Oftentimes, and we'll see this when we get to some stuff in this course later on, B0, the intercept, is thought of as the item's, you can think of it as the item's difficulty. And B1 is, you can think of it as the item's discrimination. So difficulty, because if this line moves up this way, that means I have to have more X. Whatever X is, I have to have more of it in order to get to the same 0.5 level of probability. If the line moves this way, I can have a lot less X and get to the same 0.5. So as the line moves up and the intercept gets larger, it's a more difficult item. As the intercept goes down, the item's easier. The reason why it's called discrimination is because the steep, so imagine this line being sort of flat. Well, the change in probability around the inflection point, the threshold, it can't really tell people apart very well because the probability is changing very slowly. But with a steeper slope like this, it's able to discriminate people in a very short range around the threshold, so it's a much more discriminating item. If it's even steeper, it's even more discriminating. Right? It's able to tell the difference between people in a very small range of values of X. So these terms will come back up again, and you may have heard them before, you may not have, but in terms of things like classical test theory and item analysis, these are the terms that still get used in terms of looking at individual items on a scale or something in terms of their difficulty and discrimination. And we're going to come back to that. We talk about IRT. We're going to be back to logistic functions, and we're going to be back to talking about items, difficulty, and discrimination, because it's all built around those ideas. To reiterate this idea that we typically look at model and individual item things at the same time. We did this with logistic regression as well, where there was typically this idea of a constant only model, right? The intercept only model. And then we would add predictors in to see, do our predictors add to that constant only? Are we doing a better job at predicting probabilities and things and putting people into categories with those probabilities than we are if we just use the intercept alone? So we did that. That was, how do we compare the full model to the constant? What do we use for that? What kind of comparison do we do to know if our proposed model, the addition of predictors, actually improved the model? Right. So we would use the -2 log likelihood values, right, between the models. And when we actually did that, so we took like the full model log likelihood versus the constant only model log likelihood times -2, it would give us a chi-square. All right, so we have this model comparison table in SPSS that would tell us that there was a significant chi-square, and if the chi-square is significant, it means that there was a significant improvement over the previous model. The degrees of freedom for this had to do with the number of predictors added. So meaning that if you had a constant only model and then your full model had 3 predictors, then the difference would be 3. Right? I mean, so there's 3 predictors would be the degrees of freedom for the chi-square, and it would tell you if it's significant or not. -2 log likelihood. That's going to come back up again. We're going to be looking at chi-squares based on log likelihoods in everything. I think in everything, in terms of looking at path models, looking at all this stuff. We're going to be looking at chi-square goodness of fit tests, and it's based on the same exact idea that it is for logistic regression. What about the individual predictors? So we actually looked at like those slopes in the table I just gave you. How do we test those? How do we know if a predictor is significant or not? It's sort of analogous to multiple regression, just a little bit different. I think you might be thinking of the Hosmer-Lemmy-Show thing that is a different idea. Oh, by the way, I wrote this in the wrong place. This really should be here, constant versus full. I wrote that in the wrong place in the slide. That's the constant versus full thing we did. And I sort of skipped this perfect versus proposed, but I'll give it away because I skipped it. This is that Hosmer-Lemmy-Show thing. I think it's spelled this way, where we looked at if everyone was sort of perfectly placed in terms of probabilities, where it created those deciles of risk, those 10 groups of increasing probability across the outcome, and we would look at the fit of our model versus the fit of the model if it were like perfect, and we see how here a significant difference actually was bad because it meant we were deviating from this perfect model with our proposed model. And that was that sort of Hosmer-Lemmy-Show goodness of fit test. And we used the -2 log likelihood for this constant versus full. But then we back to how our individual predictors tested. In regular regression, we would take the slope and divide it by the standard error, and we get a t. Right. For each one of them, tell us if the predictors are significant or not. Look in these tables here, the example, it's giving us B, standard error, and then what? It's not giving us a T, it's giving us a walled. We're still going to take a slope divided by standard error, but because this is a LOGIT and the standard error is based on LOGIT, these are not so typical values. We're not going to get a t-test, we're going to get something called the walled test. And a walled test interpreted very similarly, but it's actually, it distributes more like a chi-square than it does a t. So it's not normally distributed in that same way. So we can actually look at the wald test, and that we can actually test it like a chi-square to see if each individual predictor is significant. And the wald test will also come back up very shortly. The purpose of this is not to make you feel bad for not remembering stuff, even though it wasn't that long ago. But to just remind you of the things that we have talked about and how those things are, as we go forward and talk about things like a wald test and a path analysis, something like that, they're not new things. These are things we already talked about. We're just going to be using them as we go forward and looking at path models and confirmatory factor models and everything else. That the same kinds of tests that we're going to be using, you've seen before, so you not remember. That's why I'm helping you to remember now. So there's our log likelihood test. We would calculate the likelihood here. This is the actual predicted y value. This is the probability that we're predicting, right? This is the y predicted from our model. So we're taking the natural log of our predicted probability times the actual y. We're adding to that, this is the failure. This is the 1 minus y times the log of the failure probability, the opposite. And then we do that for every single person and sum up across everybody, and that gives us a log likelihood, right? Because it's the natural log of their likelihood. So another term for probability is likelihood, right? So if someone has a 0.6 or a 0.8 probability, it means they have a high likelihood of success, like by 0.8. So we're taking the natural log of their predicted likelihood multiplied by their actual score, and we're countering that with the sort of failure probability at the same time and doing that for everybody. And it gives us this log likelihood. It's going to be typically a very negative number, which is why you take a negative 2 times it to when you're actually trying to get it to be a chi-square. So this should sound somewhat familiar from, we did this for multi-level modeling. We did it again with logistic regression, right? We talked about it. So you've seen log likelihoods and this sort of idea of looking at log likelihoods as a measure of model improvements twice, in 485 with multi-level modeling and then 524 with logistic regression. I actually had originally, it was going to leave this whole table showing this. I'm like, we'll come back to it. Instead of spending all the time right now, we'll come back to how this all works later. Okay. But again, when we want to look at goodness of fit, we can take we can get a chi-square by taking 2 times. It really should be negative 2 times the difference between the models, and this idea that models must be nested. You can't compare two completely different models where you have like x1 to 5 in one model and x6 through 10 in another. You can't use log likelihood for that. It's got to be, you have like x1 and 2 predicting y, and then the next model is x1 and 2 plus 3 and 4. You can then compare those two models because the first model exists within the second model. That's what it means by nested, in order to compare them. And that's going to also be true when we look at model improvement and model fit in path models and those kinds of things as we go forward. This idea of nested models and the comparison of log likelihoods across them to see if there's a significant chi-square change. Talk about factor analysis. So this was one of the last things we talked about in Psy534. Probably one of the more complicated, and not necessarily mathematically, even though it is mathematically complicated, but because there's so many choices, there's so many options, so many ways of going about doing an EFA, that it can be overwhelming because you have different options for rotation methods, different extraction methods, different numbers of factors. There's just a lot of things. And I've mentioned, hopefully I mentioned it last semester, but I know I mentioned it in other classes and other times, that factor analysis is just it's like almost as much art as it is science. There's like the math of it, but there's also a whole art to it where you have to sort of learn how to interpret and how to sort of work with variables and how to make a decent factor structure out of items. It can be tough and it takes some practice, lots of practice. So how does an item's variance get divided up under the common factor model? So under a typical, just looking at variables by themselves, a variable has, whatever its variance is, it has 100% of its variance is part of that variable. And then under the common factor model, in exploratory factor analysis, we talked about sort of being able to divide up that variance into different pieces. Right? So we had like the total variance of an item broken up into what? What kind of variance are we actually interested in? If you're doing a factor analysis, so what's the variance that is that we are the most interested in a factor analysis? So that's what I mean. So this is the total variance of an individual item. So what do we do? That's what I said. How does an item's variance get divided up? So we bring in a factor, and we say the factor predicts these items. And we base that on this idea that there should be these different kinds of variance that exist in that item, and we're trying to identify those different types of variance, or different sources of variation. No, so you're saying that based on the options that are selected? No, I mean, that's going to contribute to the total variance as well in terms of how much people are selecting, because you have truncated items, like no one uses, say, the most extreme score, right? So it limits the variation. But that's going to limit the total variance as well, not just the other types of variance. I'm trying to see if maybe I could pick on somebody else. They're quiet people. How about Hector? Smiling face there. So what are the kinds of variance? I'll give you a hint. One of the kinds of variances is actually in the title of the slide and in the paragraph, or in the question. The name is actually in there. Yeah, common variance. Yeah, there's common variance. Common variance. So I'm trying to make it colorful. So we got common variance, which is better known as what? What's another word for common variance? It's a thing that it's a thing we're trying to estimate as part of factor analysis. So there's common variance. Well, so we'll come back to that in a second. We got common variance, and what's the other kind of variance? Right, so if it's not common, if common means that it's the variance that it shares with the factor, but it also means it's a variance that's shared between the other items on the scale, right? So it's common. It's the shared variation. So if it's not shared, what's another word for not shared? It means that for this, another word for individual? Close. Well, the total variance is the item variance. So common sounds like it's the same as everybody else, right? So if I'm doing something that's common, it sounds like it's sort of mundane. It's sort of the same. But if it's variance, it's not common. It's very different, which makes it like if I act very differently and I don't do things that are common, I'm very unique. Exactly right. So we have common variance and you have unique variance. And unique variance really means it's unique in the sense of it's just not common. All right, that's it. We also broke down unique variance into two parts as well. What would make an item's variance unique would be, well, it's either because it's literally just specific to that item, or because it is error. It's random noise. These are the two things that make up unique variance. We just oftentimes don't know what's specific to the item and what's error, so they collectively get as part of this unique variance And it's just a part of the variance of the item that isn't related or isn't shared with other items. Right, so you have the common variance, which is better known as, this is h squared. Remember that? H squared, which is better known as the communality into the item. And it's literally just the sum of all the loadings. So h squared, all the factor loadings for that item summed up, squared and summed, gives us the total shared variation. And then whatever's left, this is where things get a little goofy with language, because oftentimes in models, it's not labeled as a U, it's labeled as an E. So oftentimes people confuse these two, where there's common variance and there's error. It's true, but there's also this just specific variance that gets rolled into here, but we treat it all like error variance, but it's technically unique variance for that item. So the whole point of a common factor analysis, or doing a factor analysis like this, is to identify the variance that is shared or common amongst the items, separated from the variance that is not shared or unique. And then we can build this idea that it's like a theoretical thing, that the reason why the items share variance, they share this common variance with one another, is because they're all being driven by the same factor. So what are the components of the equation above? Instead of, we're running out of time a little bit, instead of going through the process, I sort of wrote it out a little bit already, where I just sort of labeled, these are technically, I can have used this as an A or something. These are the loadings by the factors, and we're summing them across all the factors for each item. And this down here then, even though it's labeled as an E, this is technically the unique variance. So this is the portion of variance that is due to the factors. It's the common variance that's in here, the sum of all those. This relates to the common variance. We oftentimes refer to this as error, but it technically is the unique variance. It's the part of X that is not explained by all the factors. And I already mentioned this too. How do we compute the commonalities? Well, once we do the factor analysis, we actually get the results of the loading matrix, like a rotated loading matrix, or unrotated, or structure, pattern, all these different matrices in EFA. We can look at compute the commonalities by simply squaring and summing up all the loadings for an individual item. So going back to, if we're talking about X, if it's for X1, we're going to sum up all the loadings for that same X1, all the loadings of the same variable across all the factors. We're going to sum and square them to get a commonality estimate for that variable. All right, so it's the sum of the squared loadings. And if you remember that loadings are essentially correlations between an item and a factor, each one of these then is like an R squared. It tells us percent of overlap between that one factor and the item. And as we sum them, we're getting how much each factor is contributing variance to predicting that item, or it's sharing variance with that particular item. We're getting a total variance, a total percent of variation across all the factors, which is what how we're defining a commonality, sum of the squared loadings. All right, just a reminder of how the sort of process works. Take a data matrix, got n subjects. This could be hundreds, thousands, it could be 10, whatever it is. You have a bunch of subjects, and you have a bunch of variables that you're going to factor analyze. The first step actually is, even though you're submitting a data matrix like this, the program in the background is going to convert this to a correlation matrix. And the correlation matrix is what's going to be factor analyzed, which is why if you actually find an article or something where they give you the correlation matrix, you can actually start here and do a factor analysis of the correlation matrix. So what we're going to do, go forward. We do this little thing here is like the black box fancy steps where we're actually going through the eigenvalue decomposition and doing all this stuff to get the factor loading matrix. So now the factor loading matrix is, we have all the variables. So the 1 through k that's here is now down the side. And And then the 1 through G on top are the number of factors that we've extracted. We can take this factor loading matrix, multiply it by itself, right? This is just factor loading matrix times its transpose, and that'll give us a reproduced correlation matrix. So why do we want to do that? Well, if we extract the same number of factors as we have variables, if I have 10 variables and I extract 10 factors, this process will give me exactly the same matrix. The correlation matrix I start with here will be exactly reproduced there because we're not losing anything. We didn't give up anything. We used 10 things to describe 10 things. It was completely boring. All right? So as we choose a number of factors that's less than the number of variables, this reproduced correlation matrix is going to start to be a little different than the original correlation matrix. And we can actually subtract the two of them to get a residual matrix, which will tell us in some ways where we're missing things, like where by losing some, by only retaining a certain number of factors, which correlations are not being accounted for. We can actually see where there might be some misfit to our factor analysis. So just to sort of blow up the factor loading matrix, right? If we, so this is the number of factors that we extract across the top. It could be anywhere from one factor to the same number of factors as we have items, variables. Each one of these is going to represent the correlation between an item and a factor, each thing in this matrix. So if I square each of these going across and sum them, it's going to give me the commonality, the actual percentage of common variance for that item. If I square them and sum this way, it's going to give me the reproduced eigenvalues, like the sum of variance for each factor across the items. So these are the reproduced eigenvalues, the commonalities on that side. So what's factor extraction? Factor extraction is the fancy term that we sort of use to explain this sort of the sort of black box things that are happening, the stuff happening behind the scenes, the eigenvalue deconstruction, reproducing the eigenvalues when we actually look at the model, all those things. It's all part of extraction. And for you, the user, the person who's trying to do a factor analysis, the extraction part is where you decide how many factors, and we look at things like the scree plot, and we look at the ratio of eigenvalues, we look at are all the eigenvalues over 1, all those kinds of things to then decide, all right, well, how many factors do I think I have? Let's actually limit the number of factors down to a smaller number, or I'm going to add in an extra factor to extract. It's just identifying the number of factors we need to explain the items we have. That's the factor extraction process. The problem is when we do that, the eigenvalue decomposition process is just a mathematical thing. It's just projecting lines in the space, trying to capture all the variations. So it's not trying to make the items and the factor relationships understandable. It's just trying to account for a number of the amount of variance. So rotation is literally taking the stuff in space and actually rotating them around the factors so that they actually can do a better job of explaining items. So it's trying to move them towards simple structure, where simple structure is each item loads on only one factor, right? So you don't have cross loadings and that kind of stuff. So simple structure will give you, if you have 3 factors and 7, or let's say 9 items, you have 3 items on factor 1, 3 items on factor 2, and 3 items on factor 3. There's no cross loading. It's nice, perfect little simple structure. That's usually the sort of the goal, is to get closest to simple structure as possible. So we oftentimes will rotate the factors in space to try to make them more understandable. So factor rotation is a process of trying to make factors easier to interpret, more interpretable. And there are lots of different types. The general 2 types are oblique rotation and orthogonal rotation. I started to pause to wait for you to answer, and then I'm like, I'll just answer. So yes, oblique rotation and orthogonal. Orthogonal keeps the factors independent, because when they actually get projected into space during the eigenvalue deconstruction, they actually are independent. They start off that way. So they're they're perpendicular. This is like a geometric function in space. They're perpendicular. They're independent, orthogonal. So we can rotate them, keeping them that way, or we can allow them to share space, which is the oblique rotation, which leads to having correlated factors. And you actually get an extra matrix that tells you how correlated all the factors are. So again, the whole goal of this is to try to get the simple structure as much as possible. And the rotations also change, with an orthogonal rotation, you have just the factor matrix or the factor loading matrix and a rotated factor matrix. When you go to an oblique rotation, you now have the original factor matrix, the loadings, then you get a structure matrix and a pattern matrix. Where the structure is just the Pearson correlations between each item and the factor, but there's a lot of overlap there because the factors are sharing space now, so some of those correlations are representing the same variation. So we oftentimes will interpret the pattern matrix, which looks more at where the loadings are more akin to like a partial correlation, where the influence of the other factors have been removed. So it's more of looking at the unique relationship between each atom and a factor. And it's easy to interpret, getting us closer to simple structure. The last thing is, how do we know when we have a good factor structure? Well, oftentimes you don't. that's part of the problem. When the items are interpretable, when the factors are interpretable because the items that are on there are going together, when they sort of make sense, when it fits a theory, when it fits your hypotheses, those things all lead you to knowing whether or not your factor structure is good or not, but it's never like perfect. And I've often said that one of the main things you want to see is that the factors are actually useful. There's a certain amount of utility in the factors that is useful for other things, which will then lead you to know if you have a good factor structure or not. The bottom line is you can oftentimes give 5 people the same data set and have them factor analyze, and they'll come back with 5 different structures. It's because of what they're assuming, how they're going about it, what choices they make along the way. So knowing you have a good factor structure is difficult. You want to look for, are the factors interpretable? Are they intelligible based on the items that are loading on it? And are you going to get useful factors that you can either predict with other variables, or you can predict other variables with, that they actually have some contribution to a bigger model, a bigger prediction equation? Then you have something useful, and then the factor structure is good because it's useful in some way. All right, questions about factor analysis. We're going to spend a lot more time on confirmatory factor analysis and stuff specifically. So these, we're going to talk a lot bit more about this kind of stuff as we go into the semester. That's why I didn't quite cover as much of factor analysis as I did the other 2.